Hello, so this is a revision video for AP Chemistry 3.2, Properties of Solids. Vaporization is the process by which particles gain enough energy to escape into the gas phase. In any liquid, some particles have enough kinetic energy to overcome the intermolecular attractions holding them together in the liquid, allowing them to vaporize, evaporation. The vapor pressure is the pressure exerted by the vapor that forms above a liquid in a closed container due to these escaping particles. At the same temperature, a liquid with stronger intermolecular forces has a lower vapor pressure than a liquid with weaker intermolecular forces. The boiling point is the temperature at which a liquid's vapor pressure equals the atmospheric pressure acting on it. At this point, molecules throughout the liquid, not just at the surface, have enough energy to overcome intermolecular forces and escape into the gas phase. Below the boiling point, vaporization, or evaporation, can only occur at the surface. However, when vapor pressure equals atmospheric pressure, bubbles of vapor form within the liquid. This is boiling. Stronger intermolecular forces mean a higher temperature is required for this, given a higher boiling point. Melting involves the rearranging of particles from a fixed solid structure into a more mobile liquid phase. Since particles stay in close contact in both phases, intermolecular forces aren't completely overcome. Still, stronger intermolecular forces usually mean higher melting points, although the correlation can be less direct than with boiling points because particle arrangement and packing also matter. There are different types of solid that you should be aware of for this course: ionic solids, covalent network solids, molecular solids, and metallic solids. Ionic solids are made up of positively and negatively charged ions in a rigid lattice. They're held together by strong electrostatic forces of attraction, which we call ionic bonding. They have high melting and boiling points due to the strong forces of attraction involved, and they have a very low vapor pressure because the ions are tightly bound and can't easily break away. They're brittle because if you try and shift layers for an ionic solid, like charges end up close to each other and repel. This repulsion causes the layers to break away from each other, breaking apart the structure. Ionic solids are unable to conduct electricity as charged ions are fixed in place. However, if the ionic compound is melted and so becomes molten, or dissolved in water so is aqueous, its charged ions are now freely able to move and carry charge, meaning they can conduct electricity when molten or aqueous. Covalent network solids are made up of atoms covalently bonded together, making up very large repeating structures. They have high melting points as covalent bonds must be broken to break apart the solid structure, and as covalent bonds are very strong, high amounts of energy are required for this. They're hard and rigid due to fixed bond angles in the network, and are insoluble and generally non-conductive. Graphite is an exception to this because it contains delocalized electrons. Molecular solids are solids made up of molecules held together by intermolecular forces. They generally have low melting and boiling points due to relatively weak intermolecular forces requiring low amounts of energy to overcome. However, very large molecules can have stronger intermolecular forces, meaning large molecular substances, such as plastic polymers, can still have relatively high melting and boiling points. They can't conduct electricity because no charged ions or particles are free to move. Metallic solids are made up of metal atoms that exist as positively charged ions arranged in a lattice with a sea of delocalized electrons. They are excellent conductors of heat and electricity because electrons are free to move. They are malleable and ductile because the layers of positively charged metal ions can slide over each other without overcoming or breaking the attraction to the sea of delocalized electrons. Alloys, as we've already seen in section 2.4, are mixtures of metals with other elements, which are usually metals but can be nonmetals. Alloys can be substitutional or interstitial. Substitutional alloys arise when atoms in a metallic lattice are replaced by atoms of a similar size but of a different element. For example, brass is a substitutional alloy that is made up of copper and zinc, both of which are similar-sized atoms. Interstitial alloys arise when small atoms fit into the gaps or holes in a metallic lattice. For example, steel is an interstitial alloy that contains iron and carbon, with small carbon atoms able to occupy the spaces between iron atoms. Polymers are large molecules made up of repeating units that form when smaller molecules called monomers react together. Biological macromolecules such as proteins and DNA have specific three-dimensional shapes that are defined by non-covalent interactions, so intermolecular forces like hydrogen bonding, ionic attractions, and London dispersion forces. For example, DNA is a double helix made up of two antiparallel strands held together by hydrogen bonding between nitrogenous bases. The complex three-dimensional shapes of proteins come from the interactions among amino acid side chains such as hydrogen bonding ionic bonds, disulfide bridges, and hydrophobic interactions. Exam tip here: use structure-property relationships to explain the behavior of a substance. Ionic substances have high melting points, they're brittle, and can only conduct electricity when molten or aqueous. Covalent network substances have high melting points, they're very rigid, and they can't conduct electricity, with graphite and graphene being exceptions. Molecular substances have low melting and boiling points and are non-conductive. And metallic substances have the classic characteristics of metals: conduct electricity and heat, malleable, ductile, and shiny.